I even forgot to start record. Okay, so I'm gonna re-explain everything. So now you can see my screen now. So I think you can see you can see the rules, right?
Hmm.
Okay, I didn't see I forgot to do that. So each team may bring one a 1 2 inch or smaller ring 3 ring binder as seen here. I would recommend that the first inch would be like all like the information, and the second inch would be your like previous test you took. It shouldn't just be like the copy and paste of the solutions from the test. It should be like you actually doing it and then you marking which one is wrong or right, because that way you actually like know what the questions are and like know where like which questions you knew, which questions you didn't know, and which questions like memorable. Because usually the tests are not used, rarely used, but when they are used, they're usually used for the really hard questions because those really hard questions you like know from the test because you memorize you like it was really difficult when you took the test, and that's basically why what the binder would contain: the first part information, the second part previous test. For the competition, it's basically going to be a written format. When it says questions may include one or more tasks at a workstation or a time or a time station to station format, that has never happened in Dynamic Planet. Do not expect
Well,
that.
when they say station to station format, this mean they're gonna have papers and questions, and they might so each question there'll be like four questions per station, and you have your own test, and you go around and you answer each station. So it's different pages.
Yeah, most
But we
times.
only took a practice test that was for national, so that's probably not gonna happen for regional or anything that we do.
I mean, the workstation is more like we have different parts of the paper we're going to give to you, and that it's not really like actual like experimenting. That's never happened. So basically, if you look at this like part B, participants will be expected to use process skills, yada yada yada. Basically, what it's trying to say is that there's going some questions will probably be memorization. The other part will be identification or something around that, or like diagrams that goes on identification. I would like try to like either like divide your studying into memorization or identification, because identification, it can come like in like topographic features as seen here, topographic features, or it can be like identifying like the ways. This is half diagram, like half because usually when they mention these waves, motion, height, wavelength, period, fetch, all of this stuff is usually I believe it's usually going to be shown on a diagram rather than actually like asking you like to like know the memorization. So like the thing to like actually like split your notes, or like you can split into parts next year. I'm not sure if that's too good of an idea for Dynamic Planet, but you could. One person could be like the person memorizing, and the other person could do identification, or that could be something you do yourself in your studying. And
Don't
as you
do
see
that.
here, yeah. Oh, wait, what?
Don't split it up. You should know everything.
Yeah, you shouldn't split up, but that you should split your studying to that at least or something. And then Division B stuff is right here. You can see like just Coriolis effect, gyros, temperature, topographic features, that stuff. A lot of the stuff in Division C will be tested on Dynamic Planet. So always look at the Division C stuff, because the invitationals do not care if it's on the rules or not. They just put every question they think you should be on the test, so that you should always like still take Division C into account. Like it's in every single event you probably will see. We will teach Division B stuff, but usually we'll also teach Division C stuff, because Division C is always going to be on those tests no matter what the rules say. And then like the main thing I would see from here is basically Ekman currents, and usually it would be the El Nino, and then it would usually be like the different types of oceanic tools.
Honestly, they don't use Ekman spiral too much, but it's good to
They've
have in
used
your
it
binder.
before.
You don't need to know it.
Yeah, but like there's a lot of stuff in here that have been tested that in here, yeah. And that's basically it. And then the representative activities. This is mostly just like it's half identification, the other half is like using logic mostly. The only it's actually it's a weird way to this is technically like AP test, but basically what it's trying to tell you is that you'll be given a substance, and you may have to make a theory about like an experiment. You may have to make a theory about that, or a hypothesis, or you might just have to just make a graph and diagram. Those diagram stuff you should always have inside your binder, because usually those stuff are like worth like 8 points, and they should be pretty easy once you have the diagram. And the scoring is pretty basic. High score wins. Nothing too like weird about that. And it's usually just multiple choice and some short answers, and that's it. Yeah. Do you get the rules, Jordan? Yeah, we should make a slideshow. We dynamic planet's a little weird. So besides that, for dynamic planet, I believe if we I typed somewhere. I typed exact outlining what is specifically. One of these is the correct one. Oh, so yeah. So I during my teaching on Monday I outlined like identification memorization and what topics would be. A lot of identification, diagram, circulation, gyres, fault lines, geography, and then waves. It would be waves. And memorization is like waves relation of how the moon affects waves. I forgot current. I did put currents, but you can basically you can like read. You should. I mean, it will take way too long to like. It's basically this is what I wrote, and you can see the topics about like how to split them or like just the topics themselves that you will need to study.
Okay, so I guess I'll go over what we did yesterday.
Yeah, it's up to
Yeah.
you, David.
Okay, so yesterday the first thing that we went over was gyres. So gyres, they're rotating currents in the ocean. There's five main gyres. You can see that in our binder. And the five main gyres, there's North Pacific, South Pacific, North Atlantic, South Atlantic, and I think it's the Indian, something like, and no, or Arctic gyre, something like that. But then those are pretty much responsible for circulating nutrients, salinity, and what is it? Temperature, density. Okay, hold on. I need.
What's the issue?
Sorry, my internet's cutting out.
It's fine. We have four people. We can always wait.
Can you go over gyres? I need to reload.
Okay, so gyros will gyros will basically be like spots where like it's basically just like how like as David said temperature. So I need to give you an example to truly understand it. So basically gyros, they're basically if I the first image should show a couple the first oh wait, doesn't the first image show this? Okay, so the first if I scroll down enough, I'll eventually reach this. So these are gyros. So basically if you look at that, they're just caused by the Coriolis effect, and they're basically just how like the wind curls in like a circle. And the Coriolis effect, the reason why they like turn in different directions is because of like it's like because the Coriolis effect. If you look at this, you see how like one turns one turns clockwise and one turns counterclockwise. If you see it here, and that's basically just like how it works. The south would be counterclockwise, and the north would be clockwise. And then you would need to know for like usually sometimes they might ask you for the map for the gyros, and this is basically what gyros are.
Okay, can you hear me?
Yeah, we can hear you perfectly fine.
All right. So thermocline, halocline, pycnocline. Thermocline. So these are all vertical gradients. Thermal, as in the name, is temperature. Okay. So thermocline is a rapid decrease in heat in in a short period of time. So there's three layers in the ocean. The top layer, the surface or mixed layer, and the very bottom layer is the deep layer. But in the middle is the thermocline, and it's I'm gonna share my screen. Oh, Howard, can you stop presenting?
Sure.
Okay. Hold on. Here. So here we see thermocline. This is what the graph looks like. Okay. So all it's going it's like normally going down because that's how it works, right? Because it's farther away from the sun. But then all of a sudden we see a rapid decrease. In this area where it's rapidly decreasing, it's called a thermocline. Okay. So it's a vertical temperature gradient. And next up is halocline. Halocline, halo as in salt, salinity, and this is just a vertical salinity gradient. So it's a rapid increase in salt because or this is a bad graph. Hold on. This one's better. So you can see here surface in the deep. Over here is the halocline. And then this ties in very well with pycnocline. Pycnocline is a vertical density gradient. And it just means that as depth increases, density is increasing as well. So these are all just vertical gradients based on depth. And pycnocline It increases in hand with halocline because there's more salt. Therefore, the density of the ocean is greater. So yeah, that's it. And currents, like I said before, currents they're responsible for many things, but the main things are for maintaining, transporting temperature, density, density of the ocean, salinity, and nutrients. Okay, and there's a lot of major currents, but we have a map on the binder. I'm not sure where it is. Let me find it. Hold on.
I don't think you share
All
screen
right,
right now, but
I know. There. So you see here, these are like the currents, and as you can see, they're all going in. They're all kind of correlated with the gyres. See here, this is where the North Atlantic gyre is, and here's South Atlantic, North Pacific. So as you can see, in the North Hemisphere, it's going to the right, and in South Hemisphere to the left. That's because of the Coriolis effect. That's just a deflection caused by rotation of the Earth. So in the top, it's to the right, and the bottom is to the left. And at the equator, it's all like pretty much straight because there's no Coriolis effect there since the curvature it's not it's not um it's not as curved, if you get what I mean.
uh,
Okay, so that's pretty much it.
oh
Now
yeah.
your turn.
Wait. Oh sure. So I guess we're done with the review. Wait, Jordan, do you have any questions? Okay, so if Jordan says no, so basically we'll move on to the next topic. So next topic today, well, because wait, did you go over currents? You said you went over currents yesterday, David.
Yeah, we did.
You didn't explain currents. Oh, you technically
Yeah, I
did.
did.
Did you? Oh, you didn't explain. Oh, I thought you. Wait, did you explain the different types of currents?
Huh? No,
Did you? Oh, okay.
I didn't do that
That's.
yesterday either.
Oh, that's why I was wondering why you didn't say it. Oh, okay. So basically, longshore currents. You can read this if you want, but basically, what longshore currents are is basically how they go along the shore. Well, that's basically what the name says. They go along the shore, basically, so they go in the same direction of the shore. And if you can see from this image, this is a really good image. It seems, so if you look at this, you can see the shoreline is right here, and the longshore current is basically going alongside of it.
You're not presenting.
Oh wait, I forgot. Yeah, you're right. Thanks, man. I keep thinking I'm always presenting because that's usually what happens. Okay, so basically, for longshore currents, if you look at the image here, you'll see that the red arrows point to the right, and you can see the shoreline here. Basically, longshore currents would basically mean that they were going alongside it. Another way to think about this is that well, never mind. Yes, that's basically how it works. So if you look at that's basically how it works. And then the angle or wave of approach, it it really comes at different angles, but because it like goes against the shore, it veers off to the right and left basically. And then rip currents in this case are strong channels of water that flow away from the shore. Usually what happens if this image is actually quite a good idea case for it. Well, I should this, wait, what? This image is a pretty good ideal case for it. But basically, what happens is that if I can do my whiteboard, is that say if this is that's such a bad color for shoreline. So say if this yellow, say if this black represented the shoreline right here, and you had your waves coming. You had pretend this is the rip current. What happens in the rip current is that when it hits the shoreline, it goes back this way, but because there's also another one coming here. So basically what happens is that when this is also deflected back, so what happens is that basically this would go in basically like a circle almost, and it would actually basically divert back because these two meet together and therefore push each other. But it basically goes in a circle. This is how you would look at this from above basically, and that's basically what a rip current would be. They're usually very strong currents, and that's another key fact. And upwelling is another. It's technically is a current. So basically, what happens is that it just basically brings up water and nutrients from the bottom of the ocean to the top, and that's pretty much what it does basically. It usually happens because the cold water is going up to the warm water, and that's pretty much it for the currents. So besides that, we also have tides. I need to scroll down to tides. So the only way to actually do tides is to show you an image, because it's pretty hard to understand this without the image. So spring tides are basically when the moon is between the sun and earth, and basically what this causes is that the really so if you can like so if you like think about this. Oh my god, where did my whiteboard go? Oh, I deleted it. So basically if I So basically, if I do the whiteboard, if I show the whiteboard, it's like you can see the, but you know how like the sun, you know how like you basically know how the sun is a big mass, and like how mass makes bigger gravity. Basically, what happens is that because say this is the moon, this is the sun, and then this is the earth, because these both are putting their gravitational force up this way, that's why the waves are usually greater in this case. But say now that we have like neap tides, well, the moon is like diverting the waves the other way, because without the moon you technically wouldn't have waves, but because the moon is like diverting towards the other way, what happens is that basically if you can think about this, is that the gravitational pull kind of cancels out, and that basically they're usually relatively weak neap tides basically. And yeah, that's basically it. Oh, I forgot to include this. Neap tides occur 7 days after spring tide. That's basically the only other thing I would believe is important for a neap tide. And that if you can think about this correctly, is that the moon is usually a 90-degree angle, of the sun. So basically, yeah, it can be the first or third quarter. It won't really make a difference. You just need to know it's a 90-degree angle. It's how I think of it. And now, with that said, I think we went over everything that has to do with like actual like current, waves, ocean. Yeah, I think we went over everything that belongs to that. Oh wait, oh yeah, I forgot to explain something then. To review for something, I forgot to explain this because I thought I explained this on Monday, but I don't think I explained this to Jordan. So basically, the wave itself, is usually has s, and this is like the height over time, or meters, or h for h or meters in this case. What happens usually with waves is that they usually go. If you look at this, is like a very rough diagram. Basically, they would basically like go up and down, basically like this. This or it doesn't have to cross the x-axis or the x-axis and become 0 meters, but you get the point. And basically, if we can think about, there's actually parts to label this. So this is supposed to be labeled as the trough. There's actually different parts to the wave. This is labeled as the trough. And the top part, you can just think about this as the crest. The best way to memorize this is just that the trough, like you can think of, I don't know why, but I think of boat when I hear of trough, just think of that. And then when you hear crest, you can just think of the moon's crest, just think about how high it is, and then you can think about like it's the top. That's how I memorized it. And then amplitude is just, I have no way to memorize this. It's just this is what amplitude is. It's the distance from the equilibrium. Amplitude. It's basically the distance from the equilibrium, and then wave height is just like extended version of amplitude. It's just all the way down here. This is amplitude.
Oh yeah, we kind of went over this yesterday.
What?
We went over this yesterday. Forgot to.
Yeah, I was thinking about if you. Yeah, I was thinking. Oh wait, yeah. So I think in the wave period, basically there's two. Okay, so and then there's different values that don't really associate with the wave itself. Hertz is how many like waves, how many full waves per second. Basically this means like how much like a full, basically like this would be a full wave when it goes from bottom to down all the way to that's a bad color. If I went from here to here to here, this how many waves in 1 second. So they say this is the 1 second mark. Let's call this the 1 second mark. If you look at this correctly, there's one, because what counts as one wave in this point is this. Because if you look at this is counted as one wave, and then to show you better, I'll use another color. I'll use a rainbow pen, and if you go like this, you'll see that there's actually two waves, and this is wait, not the edge part, not this west part, but all the way up, all the way to here. That's another wave, and then if you think of that as 1s, basically hertz in this case is 2 hertz. Usually waves are a lot more than that. That's just an example. And then besides this, there's also a wave period, I believe. Okay, I need it.
Period and length are the same thing pretty much.
Wave period is I believe it's the time for one
Full cycle.
what?
Full cycle.
Yeah, one cycle. You can think of there's two ways. Think of this. The textbook. Most textbooks usually say like this, but that's wait, I need a different color. I'm limited on color choices. Okay, so I'm just gonna I'm gonna erase the previous example. Hopefully you understand. Hopefully you understand it. But I'm gonna use black now. So usually textbooks show it like this as one wave. If you can see the black, they usually show it like this. But you don't really have to do that, because what really happens when you do this is that you can realize if you go this part right here. This part right here, if you look at this, wait, what happened to my drawing? If you look at this part, right here, the black part, you could just move that to this side, and that just becomes one successive wave, and that's just one wave, time for one cycle. And then the last term to know is wave speed. Wave speed is how long the wave travels per second. It's distance wave travels per second. It's basically meters per second, if anything. So all this means is that at what point s does the total distance m it travel? But this is
Howard, hertz
yeah.
is not how many full waves per second. That's wave frequency.
You sure?
Wave frequency is measured in hertz.
Oh, okay, same thing. Oh, wave frequency.
Also, he's asking what H, M, and S stand for. What is M and S? Oh, S is speed, I think, and M is, I don't know.
Meters, and this is second.
Oh.
H, this was no, literally my X and C are so close to each other on the keyboard. You have to understand that. H is I guess I'll erase H just means height in this case, height of the wave. This is the usual diagram they would use to represent a wave. Usual diagram. This is the usual diagram they would use to represent a wave. I don't see any others. That means for wave speed, you have there's a formula for that. I think I almost forgot the formula. The formula for wave speed is supposed to be, oh my god, it's supposed to be wavelength over wave period, I believe. Yeah, so it's wavelength divided by wave period. And that's basically all you need to know about waves. All you need to know about waves, you need to know about waves for now. I'll take a picture if you want. I accidentally spelled meters wrong. Meters, but basically just M represents meters of the height, and then S, this is basically the wave. Oh, there's also equilibrium. The equilibrium is basically where there's technical equilibrium. The equilibrium is basically this x-axis, wherever, well, not every case of the x-axis, but it's basically where the wave center is, dependent on the crest and trough, where the wave center is, based on the y-axis, basically.
It's just where the ocean surface is, because right now we're kind of talking about electromagnetic waves, but electromagnetic waves and ocean waves move very similarly.
Yeah.
So just regard them as the same thing, and regard the x-axis as the ocean surface.
That's basically equilibrium. Equilibrium.
Just like that. That's why you see such a long distance between multiple waves because they go underneath and then connect.
Yep. That's surface. And this is basically if you. Let me make sure I'm recording. Yeah, I'm recording right now, so I'm just gonna take a screenshot in case you guys ever want to refer to this later. But this recording will be posted later. So basically, that's basically it for wave. I believe we've covered everything for the view and news. So what could I talk? I could. You already talked about the different waves, and you already talked about tides. What else is there then? Oh, we could talk about El Nino then,
How
cause
about ENSO? ENSO.
what?
Oh yeah, El Nino Southern Oscillation.
Yeah, we could do El Nino then,
So
cause
want me to do
so
this part?
what?
Want me to do this part?
You want to do it?
Sure.
Sure. Wait, you
Okay.
want to do it? I can let you do it. Do you wanna?
All right. Yeah, I'll do it.
Okay, sure. You can do it. I'll stop my share screen then.
Okay, so you see here, um, El Nino Southern Oscillation. As you may know, El Nino or La Nina, they're like the sea surface temperature anomalies, and they're like central tropical Pacific, east like by the United States. Okay, so condition it's meant for a period of less than 5 months. It's classified as El Nino or La Nina conditions, and if it's for 5 months or longer, it's classified or as El Nino or La Nina episode. Oh. And it's normally occurred at intervals of 2 to 7 years and lasted 1 to 2 years. This is my sister. She wanted to be seen.
Camera's not even on.
Yeah, it is.
No, there's a green
Oh,
light
okay.
flashing.
Well, never mind.
Ring something?
Hold on, I have to mute for a bit.
Uh, we'll wait for David because David probably has his own way for teaching, and I don't want to interrupt him.
Yeah, my siblings came into my room. It's okay. And also El Nino, it occurs when the trade winds weaken and the warm water from Southeast Asia go to the West Pacific. Okay, so that means no more upwelling, but as a result, more rain. But as you know, upwelling is the transfer of nutrients and salt to the surface of the ocean. But now that it's not there, it's very unbalanced. And when the rain comes, it's only creating a further imbalance or further entropy. So here are the first signs of El Nino: rise in air pressure over these places, fall in air pressure over these places, right? And also the trade winds in South Pacific weaken, and the warmer rises near Peru. Okay. So because of this, the warm current, it's also known as the Humboldt current, it's replacing the cold, nutrient-rich surface of the. I mean, that's what's being replaced because that's normally nutrient-rich, but now if there's no upwelling, it's being replaced, and the equatorial current. Okay, and normally this supports a lot of food or fish, and and normally it only lasts a few weeks or a month. But if El Nino continues to last for many months, it can be detrimental to ocean warming, and it can be detrimental to the economy of local fishing because then it can cause a decrease in fish in one area, but then a sharp increase in another area. And so the Walker circulation during non-El Nino conditions, Walker circulation is seen at the surface. Okay. So they're easterly trade winds, and they move water and air moved by the sun towards the west. So and finally, this causes upwelling off the coast of Peru and Ecuador, and now it brings nutrient-rich cold water to the surface, and now it's increasing fishing stocks in places that were previously affected by it. And the western side of the equatorial Pacific, obviously warm, wet, low-pressure weather. As you may know, anytime there is like severe weather, we associate with low weather because clouds, and we also associate it with warm water because these are the ideal conditions for typhoons, cyclones, hurricanes. Get it? So all of this, it makes up El Nino Southern Oscillation. And so here we can see this. Normal conditions, it'd be going normal conditions, it'd be more even. But as we can see here, the heat is going this way rather than this way, and it's not being transferred equally. So on the other hand, La Nina, we have unusually cold ocean temperatures in the eastern Pacific. Okay, El Nino is warm ocean temperatures. So they're just the opposites, hence the names. So Atlantic tropical cyclone activity during La Nina, that's enhanced a lot. That's why during La Nina seasons, Atlantic tropical cyclones increase in frequency. So here, this table, we have the effects. Take a screenshot. Okay. So strong equatorial countercurrent. So pretty much they're similar. You can see here we have a strong equatorial countercurrent, but then here is a Peruvian current. And this would be a wetter than average winter. This is just the higher sea level in these locations. Here, there's the ridge and the polar jet stream. So jet streams, as you may know, they're the things in the air that fast-moving currents of air, and they transfer. In these jet streams, we can also there's like evaporation, and these also transfer nutrients. But La Nina has stronger than normal subtropical highs. El Nino, since it's warming, it's drier than average. But La Nina, since it's colding, it's increased snowfall in northwestern U.S. So that's like Washington, Oregon, right? And then and to sum it up, large scale warming, oceanic cooling, and they both happen in the Pacific. Okay, that's it. Pretty much it for El Nino and La Nina. The main thing you should know is this, as well as its effects on the markets and the water circulation. And remember one other thing. Remember the Humboldt current? Humboldt current is very important for El Nino because that's what's being replaced, and therefore no fish food. Okay, now okay, I'm gonna stop sharing.
Okay. Oh, okay.
Um, actually, I'll do one more thing. I'll do how to use maps and you can use tools.
Oh, maps. No, those are kind of easy to understand. It depends.
Okay, here we see this is a topographic map, okay? And I'm in rose color, so I know. So what you have to identify based off of these is their different features. So based on the ocean color, you have to identify depth. Where it's darker, it's going to be deeper because it's going deeper. And you also have to identify basins, continental shelf, continental slope, and you can tell these by the changes in the depth of the ocean. So a lot of it is also using your prior knowledge and applying it to specific situations. Like see here is a Pacific basin, right? That means that in this basin, it's going to be deeper. But on the other hand, we have the Gulf of Alaska. Gulf of Alaska is famous for the Ring of Fire being along here, and this is shape, right? So you should just know about it. And also trench canning and seamounts. These are just oceanic features that we'll go over later. Now, you can do tools, because I do not like tools.
Yeah. Okay, sure. So basically, oceanic. If once my share screen is on, oceanic tools basically they're right here. There are quite a lot more than what we have put here. Mainly because there's like a lot. Most of the time you probably have to like search up and because this is actually kind of hard to find. But to get to the main point here, basically the acoustic Doppler current profiler basically just measures like the speed and direction of ocean currents. That's basically like the thing you need to know. Like that's all you need to know. It just measures currents by knowing the speed and direction of ocean currents. Well, that's kind of repetitive, but you get it. And the next ocean tour we have here is the Bushmaster and the Chimney Master. You can just think of them like how you have like the master and how like it's chimney, like how they're really big. Just think of them as really big instruments basically. And basically these instruments are basically just like put around like hydrothermal vents basically, and they just collect like information on the wait, what? No, they basically just collect tube worms and like an associated fauna either on the seafloor or like a sulfur chimney. They're basically just being near these hydrothermal events and usually just finding like information about the sea life or like the rocks near there, or like just basically the materials or like the life under there. Cloud cards are basically just like plaster, and they just usually just understand the patterns of water motion. It's different from the acoustic current profile because that also measures the speed and it measures speed and direction. This one just measures the patterns of the motion. That you need to understand that difference. And basically the point of this is to understand basically like the organisms how they like physically what they do and basic what their patterns are because of they affect the pattern of the water motion or how the water motion affects them. And then basic and with these how this basically works is that these cloud cards, they basically just dissolve, and when they dissolve, basically scientists can basically like characterize the near bottom flow patterns. Drifters are like kind of boring, I guess. Okay, drifters basically, by you can probably tell by the name that basically they just probably they drift along the ocean surface. I mean, yeah, basically just drift along the ocean surface, and they basically just collect like information on like the ocean circulation patterns in real time, and they just drift basically as the name says. Satellites, I'm pretty sure you guys have figured out that satellites are pretty much just above the Earth's surface, they're in space, and they basically just take images and with the different instruments on them, the topographic features of oceans, and basically the map David pointed out earlier was done by the satellite, and they basically measure depth and the features basically. They also measure in terms of how the sun and moon affect the Earth, but that's why you can see right here that it says sun synchronous when the satellite passes over any given point of the planet at the same local mean solar time. It does measure some the main point of the satellite is that it measures geographic features, or sun synchronous is the other part. Then some semi-permeable membrane devices, or SPMDs, are basically just sampling devices that just like measure trace levels of like organic contaminants. This basically just measures basically the organic compounds, and usually they measure the PCBS or PHS, and basically they're just to like find like the pesticide inside the water. They're not. I guess they are important. And then the kind of the most like used one on test is sonar, and you need to know what it means. It's sound navigation ranging, sound navigation and ranging. It doesn't. It of course doesn't look like it's sonar, but like you just need to memorize that SONAR, and that's how like you memorize the sonar. Sound navigation ranging, and basically it just goes and it basically like releases a signal. It kind of functions like radar. It releases a signal or sometimes a sound, and basically sound waves like basically reflect off and then come back, and that's basically how they work in sonar. And they usually, yeah, they do kind of work like radar. They're really actually kind of really similar to radar. And then submersible collectors, they're basically mini submarines with just like a robot controller. That's how I think of them. What they basically are is they just collect samples from the ocean floor, and that's basically all they do. I think a better way to what do you call it? Submersible collectors. The reason why I say they look like a submarine is because they kind of are. So there's different types of submersible collectors like this. This is probably the most classic type. There's sometimes a human, there's sometimes a robot, there's sometimes machine control. But as you can see, all it is basically like a submarine that's a robot submarine. That's how I think of it. Like you can tell from the image what it basically is. And besides that, I believe we have one last instrument, and that's trawls. Trawls just like collect organisms, and they usually just to like collect data on like the quantitative data on like the marine organisms such as biomass, weight, and age classifications. And this just helps us help scientists figure out basically animal populations and how to prevent overpopulation or overfishing. One of either of them, and basically it's just for like monitoring just the fishing levels and how much the company should fish basically. And that's basically all of the oceanic tools. There's more actually. Isn't there more though? I bet aren't there more than this?
There's a lot more, but some of them we have them in the test. They have them in the test in the binder, so they'll be able to use that.
Yeah, I'm pretty sure there's like a couple. I was like thinking there's a couple more I remember, but yeah. And I think.
All right, I'll tell you what. I'll do one more thing. That'll be features of mid-ocean ridges. You want to do it, or should I do it?
Features of ocean. You can do that, I guess. We can rotate.
Alright.
Yeah, that works out.
All right. Here, so here, this is a good diagram of a mid-ocean ridge. For those of you that don't know, mid-ocean ridges is where blue seafloor is made. So originally Alfred Wegener thought of continental drift, and originally all continents were Pangea. And then Harry Hess later supported his theory with this theory of seafloor spreading. So this is the mid-ocean ridge, and its many peaks in the Central Valley, and magma comes from inside the mantle, and it pushes the older seafloor out of the way, and it creates new seafloor, right? So that means that wherever mid-ocean ridge is, that's the youngest floor, and as you go closer to the continents, that's where the older floor is. So here are the different features of it. The abyssal plain, this is right here. It's pretty much where you, if you were on mid-ocean ridge, is where you would walk. It's like fairly flat. Continental shelf. Continental shelf is the very flat part. If it goes out into the ocean for I think like a few hundred yards, or not a few hundred kilometers. Okay, and then after that, it sharply slopes into the continental slope. Okay, the continental slope is just like a steady incline, and they're very steep. They're also very big because here it's kind of, it seems very exaggerated. I don't think it would be this big. Normally it go like this, and then maybe like that. If you can see my mouse, like that. Okay. So this is just where it becomes like the deep ocean. And then here we have the volcanic islands. So volcanoes obviously are underwater as well. And when they some of these volcanoes, they have very high mountains. They even break the surface. And these underwater, these are not volcanoes. These are actually called seamounts. And the seamounts are just mountains that are underwater and don't break the surface. That's important. So over time, due to weathering and erosion, a volcanic island can become a seamount because it eventually will go below the water. Because there's so much salt and there's so much wind going here that eventually it's just going to keep on getting eroded away at. And then here we have a trench. Trenches are the deepest on Earth. They go very far down. The deepest spot on Earth is the Mariana Trench, and it's 11 kilometers deep. Okay, this to give you like, no human on their own would be able to just ride down there unless they had very expensive submarines. Okay, so that's the mid-ocean ridges. Mid-ocean ridges are important. Got it? Okay. And also, the largest mid-ocean ridge is the Mid-Atlantic Ridge, which is in the middle of the Atlantic. And if you look at a diagram, here, I'm going to show you. Mid-Atlantic Ridge, what happens is that new seafloor is constantly being made. All right, well, I don't like any of these. But yeah, here's the thing. So over here, we have the convection. And so the lava is coming from the mantle and going out. And so this land over here by the continental shelf, that's old. That's old. All of this is new.
Is it just me or I can't see it? I don't.
Oh, hold on.
Yeah,
See this?
Yeah.
Okay. Here, seafloor is very old. So is here. Here it's very new. And it's coming from the mantle, which is and here, see, so mid-ocean ridges, as you might know, they're divergent. It's a result of a divergent plate boundary. So these two are pulling away from each other, creating this rift or the mid-ocean ridge. And as a result of this tension, hot molten rock is, see, like going down. The convection goes with it, and then it goes up. So it's like boom, like that. Okay. Can you see? Can you see this?
You
Okay.
stop presenting. Oh yeah.
I did?
Yeah.
Oh, okay. What's so funny?
No, I didn't. I didn't laugh. Like I don't know what you're
I
trying
don't know.
to ask.
You're always smiling or something. Okay. Here's the coastal features. Use this diagram. They're always gonna have something like this. Just keep in mind that you should know what a beach is, know what the cliff is. The headland is on the cliff, is at the top where it's just about to go to the beach, but it's not. The tombolo is the spit of land that goes to like a sand island. Spit is just a spit of land, a spit of sand. The dunes, as you might know, are here, and the lagoons is when it's a feature that used to be a reef, right? But then it got so eroded away. Now it's just a lagoon with land on both sides. And I think that's it. Okay, so I'm stopped.
Do you want to end it here for today, or do you want to continue on? Or
Yeah, so I think we're done for today. Good job. Here's what I want you guys to do. If you haven't taken the first test that I posted a long time ago, let me see. Lesson 1, I want you to take that.
oh, next
Okay.
time we should explain reefs. We haven't done that.
Reefs, I did that on the
Oh,
second,
you should
first or
review
second
that.
day.
You should review that then. But yeah.
Okay, quickly let's do reefs. Okay? Reefs, there's 4 stages of reef, okay? First stage, oh, come on. First stage is the fringing reef. In the fringing reef, we see that there's an island above it, but it keeps on going down. Hawaii, right now, it is currently a fringing reef. Millions of years from now, it's probably going to become a atoll. So then, these coral reefs, they're attracted to the hydrothermal vents that are coming below from the mantle. So that's why coral forms there. So over time, as it's eroded away from the top, it'll become a barrier reef. In the barrier reef, um, it's enough for coral to grow still because there's enough hydrothermal vent heat, but the coral is creating a sort of barrier around it. And then as it's eroding even more, it's like only the traces of an island that it once was, and now there's just a lagoon here that is see here, this has the higher density and higher salinity. This is going to be almost freshwater, this water. Then there's a lagoon here, and the coral is still there, but the coral will eventually die unless it's still getting enough heat from the hydrothermal vents. So that's it. You just have to remember the stages. Okay. Jordan, can you put your email in the chat so I can share the binder with you? All right, Howard, you can stop recording now.
Okay.